All right, guys. Shh. Let F of T measure the level of oxygen in a pond where F of T equals 1 is the normal unpolluted level and the time T is measured in weeks. When T equals 0, organic waste is dumped into the pond, and as the waste material oxidizes, the level of oxygen in the pond is F of T equals blah, blah, blah. What percent of the normal level of oxygen exists in the pond after 1 week, after 2 weeks, after 10 weeks, and what is the limit as T approaches infinity? So none of this is limit until the last question, okay? It's just normal, like, plug in. So our function F of T is T squared minus T plus 1 over T squared plus 1. And because I'm lazy, I'm gonna put it all on my calculator at one time. But I don't know where I laid my calculator. I don't know, whatever. I just remember with my phone. For me? No. I'll just lay my pre-calc book on top of it because I'm gonna use it in a minute. All right, go into y equals and put in your function x squared minus x plus 1, and then x squared plus 1 on the bottom. Again, with this, make sure that your table is on ask. If you're using my calculators, I think they switched them back first period. So if you need to check it, go ahead and check it. And then it said after 1 week, 2 week, and 10 weeks. And then I don't have to work really hard. Okay. If you want to put those as decimals, we're going to. I'm just going to write them down for a minute. So F of 1 is 1/2. F of 2 is 3/5. And F of 10 is 91 over 101. Is everybody okay with how I solved that? And I did it all at one time instead of plugging in multiple times. That just takes too long. 1/2, you know, is 50% polluted. When you plug in 3/5, you get 60% polluted. And then 91 over 101 is 90% polluted. So there's those A, B, and C, like the 1 week, 2 week, and 10 weeks. Then the last one says after 10 weeks, what is the limit as T approaches infinity? So we want the limit as X approaches infinity of T squared minus T plus 1 over T squared plus 1. I can't factor anything out. If we think about the limit of infinity, T squared causes the U shape. That's going to infinity over infinity. So we have to do what? What did we have to do yesterday? Yeah, divide it by which one? T squared. So we're going to take everything. And why do we pick T squared? It's on the bottom. Good. T squared over T squared is 1. T over T squared is 1 over T. And then 1 over T squared. On the bottom, 1 plus 1 over T squared. And then we take the limit of each part. So what's the limit of 1? The limit of 1 over T. 1 over T squared. On the bottom, 1 and 1 over T squared, which gives us 1. What is 1 as a percentage? 100. 100%. Remember, 0.9 is 90%. So 1 would be 100. Is everybody good? That's it. Super easy problem. Flip it over. Infinite limits at infinity. Many functions do not approach a finite limit as x increases or decreases without bound. For instance, no polynomial function has a finite limit at infinity. The next definition is used to describe the behavior of polynomial and other functions at infinity. So let f be a function defined on the interval a to infinity. The statement, the limit as x approaches infinity of f of x equals infinity, means that for each positive number m, there is a corresponding number n greater than 0, such that f of x is greater than m whenever x is greater than m. This is not going to make sense yet, but it will when we do the examples. So same thing for the next one, except for it's equal to negative infinity. So the limit as x approaches infinity of f of x equals negative infinity. Means that for each negative number m, there is a corresponding n greater than 0, such that f of x is less than m whenever x is greater than m. Similar definitions can be given for the statements. Rewrite those two limits with negative infinity. So the limit as x approaches negative infinity of f of x equal to infinity, and the limit as x approaches negative infinity, f of x equals, negative infinity, sorry. Four more examples, we're done today, and you can have your homework. Finding infinite limits at infinity. Find each limit. The limit as x approaches infinity of x to the third. So this one, as x increases without bound, x to the third also increases without bound. So if you're not sure what that means, when we graph x to the third, as far as we can go to the right, this one is increasing to infinity up. Okay, everybody understand that? So this says, as far as we can go to the right, it's not bound by anything, then x to the third is going to continue to increase. So the limit as x approaches infinity of x to the third is going to be infinity. So remember, this is the right side because it's going to positive infinity. If we look at the left side of this function, no matter how far we go to the left, what's going to keep happening? So the same thing applies, except for it's decreasing without bound. So the limit as x approaches negative infinity of x to the third is negative infinity. Perfect. All right. I want you to see the difference in the next ones. Let me graph these for you. 2x squared minus 4x over x plus 1. I'm going to zoom out a little bit. Remember, rationals always have like two little parts to them, whether it's side by side or it's opposite of each other. So that's why I zoomed out so you could see the second part. What's different about this one compared to the other ones? Now, seriously, we're talking about this like I'm not trying to trick you. Like literally, what do you see that is not the same as what you've been seeing? Okay, so it's got a vertical asymptote. The other ones weren't connected either. I'm not quite sure what your definition of connected is in this sentence. What do you mean they're not together? Okay. If somebody understands what he's saying, let me know. I don't mean that in a bad way. Like, you know what you're talking about. I don't. What else do we see? Let me help you with a normal one. Or even 1 over x squared. You can't really see either one of those. Hold on. And it's not the fact that they're beside each other because, let's see. No, why is it not going to touch the x-axis? Like the other ones don't touch the x-axis either. Tell me what's different. And remember, this one that it's about to graph is like this. Does everybody understand that? What's different? So the first one has two things. It has a vertical asymptote, or the red one has a vertical asymptote and a what? Horizontal asymptote. We're literally like just talking about this. I'm not, again, trying to catch you or anything. I want to see if you'll come up with this by yourself. So it has a horizontal and a vertical asymptote. What about this one? We heard vertical asymptote. We can see that at 0. There's two what? Any other way to graph it separately? Okay. I do like that. And sometimes that happens. It just depends on what it is. It just depends on what it is. Remember, because we can have the 1 in the top and the 1 in the bottom, like in quadrant 2 and quadrant 4, or even in quadrant 1 and quadrant 3. I told you that can happen. The first ones just happen to be in quadrant 1 and 2. What's different? I want you to see it. I'm telling you, it has to do with asymptotes. We have a vertical and a horizontal in the first one, or in the red one. What do we have in the blue? We sure do. Can everybody see the diagonal? You guys see that? So you've talked about this before, but you probably don't remember that you talked about this. It's called a slant asymptote. Everybody okay? It's okay if you haven't remembered where code is at. So that might be something that got pushed to the side. So this is why I wanted to talk about it to make a big deal about it. But I want you to see it. Okay. So you've probably been looking at that for a while and not saying anything. So I appreciate you. No, just kidding. You're fine. So you guys see that diagonal, that slant asymptote. When you see that, it's a special case. Okay. So that's what I want you to get. So when you graph it and you see it, it's going to be a special case. And I'm going to go ahead and write that down, but it's a slant asymptote, or it has a slant asymptote. What causes that slant asymptote is the fact that we can't factor this and cross anything out. It will not reduce, and it has that +1 in the bottom. Okay. So when we look at this, what we have to do is you got to think way back to math 3. So I know I taught it, so don't tell me I didn't. Those of you that had me, I don't know if anybody else, they should have taught it. We have to do long division on this because nothing will factor out. It's not hard. It's not. Those are easy ones. These are easy ones. Okay. So the reason that we have to do the long division is because long division tells you where your slant asymptote is. Do I understand that? All right. Why is that important? Because when we get into 4-6 and we're graphing, you may need to know a slant asymptote. How do you find it? You do long division. Okay. So that's what we're going to do. So you take the bottom, like old school elementary division, 6th grade division. And again, I taught you this if you had me for math 3. How can I get x to look like 2x squared? What can I multiply it by? 2x. Everybody good? Just like old school, you're going to multiply it down. 2x times x is 2x squared. If those are the same, you know you're doing it right. If it's not the same, you got to fix it. Okay. Then 2x times 1 is 2x. In old school division from here, you subtract them. So I taught you to change the signs so that the first 2 will cancel out. And then you add the back 2. -4 plus -2 is -6x. How do I get x to look like -6x? Multiply by -6. So when I distribute, I get -6x minus 6. Get them to cancel out. And then what is this thing? It's a remainder, right? Is it right good? What did I do? No, I didn't change all my paper. Sorry, y'all. All right, so I have a remainder of 6. So this is how we write our function. Whatever we have at the top, 2x minus 6. Our remainder divided by what we divided by. So again, that's from math 3. So then we're going to take the limit as x goes to infinity of 2x minus 6 plus 6 over x plus 1. I'm going to put this in our calculator. Graphing it, it'll take a minute. It's the same thing, right? Did I see it? Same thing. I'll tell you what the difference is in just a second. We're looking at the right side. So I went ahead and zoomed back out. What's happening as we go to the right? Okay. Why did I make you do the long division? You have a slant asymptote at y equals whatever happens before the remainder. Why is it important that you know how to do that? Again, for 4-6 when we get into that. So if you needed to graph it, you may have a question that asks you, what's the equation of the slant height? Okay, if I put that equation in, no, that's not what I wanted to do. 2x minus 6 plus 6 over. Say what? So I put in the 2x minus 6. So this. And it will never touch that, just like it won't touch any other asymptote. Got it? So that's that thing that it won't touch. And if I zoom out, you'll see it on the other one as well. But we only cared about the positive because of the positive infinity. And you'll see it'll get really close to this, and then it'll be in between them. Everybody good? So again, if they ask you what the equation for the slant height is, or the slant asymptote, sorry, then that's what you're doing, long division. So on this one, it's the same thing as it approaches negative infinity. What are we going to have? It is going to equal negative infinity. It is the same function, so we don't have to do the long division on it. But again, it has a slant asymptote at y equals 2x minus 6. Any questions? Write down your homework. In the pocket. Just kidding. I'm just kidding. The only time I'll ever tell you no to the bathroom is if we're under code blue or something.